Allora adesso cominciamo con Camilla Cattania che parla da remoto e poi ci sarà l'intervento di Paolo Negro.
Today I want to give you a broad overview of earthquake research. And I hope to show that earthquake science combines a lot of different disciplines, physics and geology, and it also combines questions that are useful for society, and also questions that are interesting from a scientific point of view. So I really hope to be able to give you a broad overview of the field and touch on these different aspects. So I want to start from an application. So I'm showing here a global seismic hazard map. So what we're looking at here is essentially earthquake risk. We're not thinking about earthquakes from kind of a scientific point of view, but instead we are thinking about the consequences. And as you can see, we have regions where we have these red colors or orange colors, which have higher hazard. What does hard hazard actually mean? I should show what this scale shows, but it's very small. So I'm going to zoom in here and we can take a look at the quantity which is being shown in this map. We are looking at peak ground acceleration. So this tells you that the quantity of interest when we're thinking about seismic hazard has to do with how fast ground motion occurs, how fast ground moves. And what we're looking at here is essentially probability that a given value of peak ground acceleration is going to be met. To give you another idea of what ground motion looks like, here you should see a video. And here we're going to look at ground velocity. So, of course, acceleration is simply the time derivative of velocity. And I want to give you an idea for what the ground motion looks like for a typical earthquake in Italy. So this is a simulation for ground motion after the Irpinia earthquake in 1980. It is quite a typical earthquake in the Apennines. I could have shown many similar examples from more recent years. And I want to point out some of the peculiar aspects about this earthquake. So what you can see here is that we have these three different faults have been highlighted. We had three different events, one at 0 seconds, one 20 seconds later, and one 40 seconds later. So basically, this tells you that sometimes earthquakes can be composed of many smaller earthquakes. And when you have many faults near one another, you want to understand how this can take place. Next, we're going to look at the ground motion. So anything in red tells you that the ground motion is upwards, and anything in blue tells you that the ground motion is downwards. So what we're looking at here are seismic waves propagating from the earthquake right here in the center. You can see that they spread in a circular way, very much like waves would do, say, at the surface of a lake. And I want to point out a couple of things. So first of all, if you're further away from the earthquake, you will see that these colors are muted. What this means with these scales, it means that the ground motion is not as vigorous as it would be. The velocities are lower than if you were near the center. I also want to point out that if you were at one particular point, you would see these red and blue colors alternating. So what this is telling you is that earthquake motion doesn't just happen at once, but instead it's a wave-like motion. So you have this wave movement that basically can continue for a longer amount of time. And basically understanding what gives rise to this wave-like motion is very important when we're thinking about seismic risk. So again, to summarize some key features here, we see that the earthquake is composed out of three smaller earthquakes. And this again gives you an idea of some of the questions that earthquake science can address. We see that the motion is a wave-like motion, and that the amplitude of this wave essentially decreases as you move further and further from the earthquake, as one would expect. So we can basically break this problem into three pieces to better understand each of them individually. One part is the earthquake itself. So here we are talking about what we call the earthquake source. We are interested in the way that faults move, and we really want to understand why did the earthquake happen, why did it propagate, why did it jump between different faults? We want to understand also why do earthquakes happen in certain locations more than others, and kind of going back to this map, the difference between these colors, it's largely due to the fact that some regions have much more earthquakes than others. And so one question for earthquake science is to identify these regions. One question, as I said, is to identify individual earthquakes and understand how they might evolve. So why did we have these 3 events in such a short amount of time? You could have had a smaller earthquake, and then you could have waited a week, and then you could have had these events not happening in such short succession. And so that's something that's a very active area of research right now that earthquake scientists try to understand. And then we also have other practical problems. And I should say this is a short list. I could have picked many more. But another important question we can ask as earthquake scientists is, what is the maximum earthquake magnitude or size which we can expect in a given region? And that's something that, as you will see, will also go into understanding the way that buildings might, like how strongly buildings might shake. Okay, so we have the earthquake. And then we have wave propagation. So you saw these waves propagating along the surface in this kind of circular way. This propagation also happens underground. And we basically have this behavior. So we saw that if you go further from the earthquake, the amplitude decreases. We have attenuation of seismic waves, but you also have waves encountering surfaces and other structures in the earth, which can change them and essentially modify the frequency content and have some effect on the ground motion. And then the third ingredient is the site. Site is essentially a combination of very local structures. So it could be something like the presence of sediments, the rock types in a specific region. We're really thinking in a local scale here, as well as the presence of buildings and such. And so that's kind of how we split the earthquake problem and the seismic hazard problem into 3 components. I would say that wave propagation is the easiest part of this problem. It's something that we understand quite well from theory. This comes out of elasticity, and essentially waves have been well understood in physics for several centuries. So I think that this is the piece of the puzzle that we understand the best. Now, the more local effects, and specifically thinking about buildings, will be very much the subject of the second half of today's conference, and when Paolo will discuss more about that. And my talk is going to focus on earthquakes, so the source of seismic waves. I want to think of this from a pretty broad perspective. So I'm first going to give a brief introduction to plate tectonics and understand what is the main driver of earthquakes on the Earth. I then want to tackle the question of earthquake prediction and briefly explain, if I can, why earthquakes are so difficult, or I would say impossible to predict. And in fact, this is not the question that we ask in earthquake science. And then I want to give you one example from my own work to give you an idea of the type of questions that we can answer and how modern data can help us with those. So I showed a map earlier of seismic hazard. So that tells us how fast we expect the ground motion to be at different locations. And here I am showing a map of earthquake locations. So each dot on this map shows you one earthquake. And what you can see is that earthquakes are not distributed evenly, but instead they are located in very specific locations in the Earth. So we have, of course, earthquakes in Italy, Turkey, Central Asia. We have regions with very, very little earthquakes, like North Africa here. And then you can also see that we have this large number of earthquakes, essentially all around the Pacific. Sometimes this is called the Ring of Fire because there are both earthquakes and volcanoes, but there is a lot of activity all around the Pacific. We see South America. Here we have the San Andreas Fault, and then all the way to New Zealand, Japan, and so on. So if you look at this map and then you compare it with a map of tectonic plates, you will see that earthquakes essentially tend to occur near plate boundaries. So they don't happen typically right in the middle of a plate, but they mostly happen when two plates meet. And so you can clearly see these plate boundaries going all the way around the Pacific. And then you can see that we are quite close to a plate boundary in Italy as well. Plate boundary actually moves like even further up north. And so plate tectonics is really the main ingredients when it comes to earthquakes, but it wasn't even discovered until the mid to late 60s. So this really shows you that seismology is a very young science. We didn't even know about the most fundamental process until relatively recently. So I want to give you a couple of examples of what happens when you have these plate boundaries. Sometimes the plates move horizontally next to each other. This would be a classic example is the Sant Andreas fault, where you have this horizontal movement. And then you have other situations in which you have one tectonic plate essentially sinking under the other plate. And that's basically because this plate is heavier, and so it wants to sink under the other plate. And so when where the plates meet here, you have this interface, and that's where earthquakes can happen. And I will mostly focus on this type of plate boundary today. So I told you that earthquakes happen because plates are moving next to one another, and this movement can cause plate motion. So then, when this was first postulated in the 60s, there was no way to actually measure plate motion. And so the question is, can we measure plate motion today? And the answer is yes. I think most of you probably have a mobile phone in your pocket right now, and this mobile phone will have a GPS receiver that can tell you where you are and how fast you're going. And it turns out we can do the same with tectonic plates. So we can measure the position and the velocity of tectonic plates, and we can do that really quite precisely, down to even velocities of only a few millimeters per year. So this has essentially confirmed plate tectonics. And so now we don't only know where the plates are, but we also know how they're moving. And so all these arrows here are showing the movement of tectonic plates relative to one another. Okay, so we know about plate tectonics. It's a very well-established theory, and we can also measure plate tectonic motion pretty accurately using GPS. So then you may ask, if you know that plate tectonics causes earthquakes, and if you can measure how fast the plates are moving, why can't you predict earthquakes, right? It seems like maybe we have all the ingredients. And it turns out we don't, because plate tectonics is the main driver of earthquakes, but it is not the whole story. And I want to go through a couple of examples that show that we have more than just plate tectonics going on. And so to do that, I'm actually going to move away from the Earth for a while and think more broadly about places where we see quakes, even though we don't have plate tectonics. And I say quakes instead of earthquakes because these are known as moonquakes for the moon. This is an example of a fault on the moon, on the surface of the moon. And moonquakes have been recorded by seismometers that were deployed during the Apollo mission. But the moon doesn't have plate tectonics. And so if plate tectonics is causing earthquakes on Earth, why do we have them on the moon at all? So for the moon, it turns out the moon is very, very slowly shrinking. And as it shrinks, the surface has to move in order to allow for this shrinkage to happen. And so we can have earthquakes, in this case, due to cooling. Cooling is what's causing the moon to shrink. So this tells you if you have some temperature effect, it can by itself cause earthquakes. Another example from the solar system is Mars. Marsquakes have been recorded, and again, also for Mars, some evidence of tectonic faults has been seen at the surface. And on Mars, this has been explained by the presence of volcanoes. So even though Mars does not have plate tectonics, it has volcanoes, and they can cause quakes as well. And we actually don't need to go that far to see evidence for earthquakes caused by volcanoes, because this happens on the Earth as well. There are many examples from Japan, South America, and here I took an example for southern Italy. Campi Flegrei actually is having a lot of seismic activity recently, which is due to magmatic activity at depth, and so that's something that we see on the Earth as well. These are just some examples. There are many other factors that can trigger earthquakes. So sometimes you can have earthquakes nearby. We saw this example for Irpinia. When you have many faults, you have an earthquake on one fault, and then an earthquake can happen on a nearby fault. You can have earthquakes happening quite far, but the energy gets transported by seismic waves, and that can also cause earthquakes at some distance. And we also have human activities. So, for example, fracking can cause earthquakes. Any activity which injects fluids in the ground can cause earthquakes. And these are just some examples. And the problem is like all these things are quite hard to measure. You don't know exactly what is going on underneath the surface. And so even though you know about tectonic plate motion, it is impossible to monitor every other possible source of forces and stresses in the Earth, which basically makes prediction very hard. So plate tectonics is quite effective at telling us which regions are going to experience the largest earthquakes. But once you add all these additional factors, which can also trigger earthquakes, then it becomes impossible to predict the exact time. Okay, so I want to go back to the questions that I had earlier. So we cannot predict earthquakes, but again, using plate tectonics, we have a good idea of where they might happen. We can ask, how do faults that are near one another interact to essentially produce sequences of earthquakes instead of just individual ones? And this is a very active area of research that I've also been working on, but I will not have a lot of time to discuss today. And then another important question we can ask is, what is the maximum magnitude that we may expect in a given region? And that's where I want to focus a little bit more on my own research and some work by one of my students to think about this question. And I hope to show you that we can combine what we know about plate tectonics with some physics about how rocks deform to tackle this type of question and get a better understanding for earthquake size. Okay, so plate tectonics again. Here I am showing the case in which you have a plate which is mostly composed by oceanic rocks. So you can see that this is mostly underwater. An example, this could be the Pacific plate in the northern part of the Pacific. And then this plate essentially sinks under this other plate here to the right. And this would be a continental plate. And basically this happens because this plate here on the left is heavier and it will tend to sink. A couple of processes that are important here is that the oceanic plate exists because we have hot magma rising from the mantle. So the plate essentially forms here in the ocean. This is the mid-ocean ridge. There is a mid-ocean ridge in the Atlantic as well. And then the plate moves here to the right. And it is important to think about the temperature of the plate. And so I want to spend some time thinking about that, and the reasons will become clear soon. So at the mid-ocean ridge, this is the place where we have hot magma rising from the mantle. Temperatures are very high. We have hydrothermal activity there because you basically have all this hot magma very close to the surface. And so we have very hot material here. And that's what happens here when the plate is first being formed. And then as the plate moves to the right, it will tend to cool. After all, it is in direct contact with seawater, which is much colder. And so then you have this very hot region right here. The plate then cools down, but then the plate will start sinking again under this other plate. And we know that temperatures increase with depth in the Earth. And so as the plate sinks, it's going to heat up again because it is surrounded by hotter material in the mantle. And so we basically go from cold material down towards hotter and hotter material. So now the reason I'm telling you this is that this temperature really changes the way that rocks can deform and the way in which they will behave. So I'm going to give you an example. When I want to think about the way that rocks deform really slowly. They can take, millions of years, and we don't have that much time. And so instead, I'm going to take a material which is somewhat similar to rocks, but everything happens much faster. So I can show you a video in a few minutes. This material is honey. So we're going to look at honey at two different temperatures. And so what you can see here on the left, we have colder honey. There is a sphere in here, and you can see that the sphere is sinking really slowly. And that's because this honey basically has a high viscosity. It really flows quite slowly. And on the other hand, the same honey, if it's heated up, here on the right, you can see that, if I kind of go back, you can see that these spheres are now sinking much faster. And what this means is because the honey is hotter, it is much less viscous, it has a lower viscosity, and it can flow much faster. And that's an experience that you can easily reproduce in the kitchen. So something similar happens to rocks. So as we go deeper and deeper in the earth, we find that rocks they can essentially flow much more easily. They become more, they have a lower viscosity, and this basically allows them to accommodate all the plate motion by flowing without ever breaking. Whereas if you are at a shallow surface, rock is much colder. It will not flow easily. And the only way that it can move when the plates are moving next to, as the plates are moving, is essentially by breaking or sliding very fast during earthquakes. And so that's the idea as to why temperature is so important. So we know that temperature really matters to many processes in the earth. And so this hypothesis was put together in the 90s. And based on a number of rock experiments, the idea was that we have this critical temperature of 350 degrees Celsius, where you basically have a transition from earthquake behavior. So anything colder than 350 and shallower is going to give you earthquakes. Whereas below this critical temperature of 350, as we go deeper, rock surfaces are essentially moving fast enough by flowing that you're not going to get any earthquake because rocks can just accommodate motion by flowing. So why does this matter to earthquake risk? I'm going to give you a couple of examples. So let's say that you have your tectonic plate sinking right here. You can find out where this 350 degrees temperature occurs. And then you can say, okay, that's where I expect earthquakes to happen. And you can say the earthquake is going to go all the way from the surface, all the way down to this temperature, which basically tells you how large this earthquake can be in extent, how many kilometers they're going to get. And then this is also related to the earthquake magnitude. And then there is also another reason, which is the fact that we often have this oceanic plate. Well, the oceanic plate is under the ocean, right? And then it's sinking under the continental plate. And this is where we have towns and cities. And so the extent of these earthquakes can determine how close the earthquake will be to these inhabited regions. And this really has to do with this geometry that, the deeper the earthquake goes, the closer it can be to buildings here. Okay, so we have this hypothesis. I want to stress that in the 90s, when this was proposed, it was a hypothesis. It was not something that was that easy to test. So the initial paper looked at some earthquakes. And of course, what you want to do to test this hypothesis is you want to look at different places in the world and then look at where earthquakes happen and then see if the location of the earthquake matches your theory about the temperature. And that's what they did in this paper. But what I want to highlight is that, so in this plot, we're looking at they basically counted the number of events of earthquakes at different depths. I want to point out that we are dealing with pretty small numbers. So the number of earthquakes that people studied initially for this work was not particularly high. We're only looking at few tens of earthquakes for every particular 5 kilometers interval, and not that many earthquakes in total. And if you want to test the theory, you want to have more data than that. So the reason that we did not have that many earthquakes was that the seismic networks were relatively recent and also not particularly large. So this is an example for one global seismic network. So each dot here, it's a seismic station, and that's where earthquakes can be recorded. If you don't have a seismic station, you can't record it. You're not going to find out the depth. And in 1990, this network had 24 stations. And then the follow-up network in 2023 had 150 stations. So you can see that now we have much better coverage, which means that we can work with much better data sets. And so now we can use a much larger number of stations, which means we can get a much larger number of earthquakes, and we can really find out the exact depth, and then we can test this hypothesis better. And so that's what my student did. That's a paper that we just published. And basically what he finds is that this idea that 350 degrees controls the depth of earthquakes everywhere doesn't really work. In this plot, we are showing the temperature where earthquakes are seen, the maximum depth. But here we're looking at temperature, and you can see that in some places, earthquakes can happen at much higher temperature than 350. We have like 450 degrees or 500 degrees or so. But in some other places, they actually don't even go that deep. They actually remain even shallower at about 200 degrees. And so it seems like this idea of one temperature controlling depths everywhere isn't really working. And so what my student, Liam, found is instead, earthquakes always seem to reach the same depth. Instead of just reaching 350 degrees, they always seem to arrest at around 50 kilometers depth. And this depth does not depend on temperature. Now we have a problem because I told you about the theory of why we expect temperature to play a role, right? So what we expect from the theory is that rocks flow more easily at higher temperatures, and so it is surprising that we don't see any effect of temperature when we look at the data. So then what we have to ask is, which rocks are we considering? And the example I gave you earlier when we had this comparison with honey, this works really well for some rocks, but not for all rocks. And it turns out that when you have plates sinking in this way, you have many different rock types because first you have volcanic rocks. They form here when magma is rising from the mantle. And then you have sediments. So you have rivers bringing sediments onto the ocean floor. So you're going to have another type of rock, which is called a sedimentary rock. And then everything is sinking to very high pressures and temperatures, which is going to modify the rocks again, and you're going to have what's known as a metamorphic rock. So we have many rock types, not just one. So what you can do then is you go to the lab, you take many different rock types. And so that was the key here. I'm only showing 4. We looked at many more, but you can look at data that people have collected from the lab by considering all these different types of minerals. And for some of them, we see that indeed they have this temperature sensitive viscosity, just like honey, just like everybody had assumed before. But it is also known from experiments that some rock types, they basically flow in the same way regardless of the temperature. And these are a couple of examples, talc and antigorite. These are 2 rock types that you might expect for this type of earthquake. So this is one example in which we can take the data for antigorite, and now we can say, okay, if you take this antigorite where temperature doesn't matter very much, what depth of earthquakes can you predict? And this is shown here in orange. So in black, we can see the actual data where earthquakes happen. And in orange, we can see the prediction for this particular rock type. And you can see visually that they are pretty close. So to summarize this work, we have a better understanding of the extent of earthquakes. And because we have better data, we were able to test an old hypothesis. And it turns out this hypothesis was actually not working. It was not right. And we now have a better understanding. So instead of 350 degrees Celsius, we know earthquakes tend to be located at 50 kilometers depth and above. And we also identified a reason why that should be the case, which has to do with these particular minerals that deform in ways that do not depend on temperature. Okay, so I want to summarize by just pointing out how when you think about earthquakes, we're really combining a lot of spatial scales. You're thinking about processes that happen on individual minerals, but they're also driven by plate motion on a scale of like hundreds of thousands of kilometers. And we're also combining physics and geology. So it's a very like multi-scale and interdisciplinary science. And then I also want to point out that we have better and better data that now allows us to better test hypotheses. And I'm going to now kind of move to or introduce, if you will, the second part of this talk. There is a saying we often hear in seismologists, which is that earthquakes don't kill people, buildings do. So the work I showed is aimed at better understanding earthquakes, which I believe is very important. But don't forget, earthquakes are the first step to ground motion. And we also need to understand what happens in between. And at the end of the day, it's also the way the buildings respond to ground motion that's going to determine the outcome. And so with this, I will end my part of the conference and hand it over to Paolo.
Good evening. Let me first congratulate Camilla on her presentation, which I found very informative. Afterwards, we will have a discussion about the two sides of the coin, let's say. What I like more now to no way. I try to turn the volume of your laptop off, but it doesn't change. Okay, as long as it is not recorded, we can stand that, or don't we? Okay. Again, congrats for Camilla. What I liked more was the part about uncertainties, to stress that there is on the side of the seismologists still much more to learn about earthquakes, and somehow we'll do the same for my side. I want to convince you that even designing buildings to resist earthquake is a new and complicated affair. That's why I want to stress the importance of how difficult it might be sometimes to devise a simple way to design buildings to be resistant to earthquake. This is to some extent surprising because mankind has started building shelters for thousands of years. And what I like to mention is the Hammurabi Codex. 4,000 years ago, people already were caring about having buildings safe. As you can see, Hammurabi decided that if somebody had constructed a house which collapses, that implies capital death. It is not so now, but again, there is a role, a responsibility in making our civil engineering structure safe. Why that? Well, the reason is evident from what Camilla said. There is a different time scale for what happens inside the Earth and the way we see these effects. That explains why there are historical evidence of earthquakes having killed people thousands of years ago, but our memory is not always stuck to that. From the beginning, mankind has tried to develop building and design techniques to improve the quality of our constructions, and cathedral is an outstanding example. But theoretical view to how materials, structures, buildings behave is relatively recent. We might say that Leonardo started investigating what happens within a structure when an earthquake takes place. And the sentence there is quite reasonable. It's a matter of connecting the walls, of putting chains connecting the vertical parts. It is not far from the way we intend it now. Some examples of smart solutions found by trial and error are also evident. One good example is Santa Sofia in Istanbul, which resisted so many earthquakes. By chance? No, most probably because it had a lot of buttresses which are horizontal and connect the structure against the main component of the earthquake. But moving to a practical way to address the issue, believe me, the discipline is very recent. One of the first treaties dealing with earthquakes was from the last century, and it was, to many extent, grossly wrong. Why? First of all, for what Camilla said, the idea of what happens inside the earth and what the consequences could be tended to be very naive from the beginning. From Kircher, there was the idea that the earth functioned in a completely different way, where people knew about volcanoes, and it was easy to imagine strange mechanisms inside. Even when the famous Lisbon earthquake took place, the knowledge about what could have happened under their feet was the one you see in these pictures. Bubbles originating from inside the earth and causing the movement of the earth. So the main approach was mostly the one which was taken by mankind those centuries. Think that there could be a reason related to God for such disaster taking place. So the evidence of a fresco from Giotto in St. Francis Cathedral depicts exactly what people thought about the origin and the reason of earthquake. Indeed, St. Francis is not the saint to pray for being protected from earthquake. That saint is Saint Emilius, a bishop of the 3rd century from Ascoli Piceno. They say he prevented the town from being distracted by an earthquake, so he's a good saint to look for, which is something that people did. This is the pray to ask for a protection of Saint Emilius. Well, I'm an engineer, but proudly, you never know, I have an original print of Saint Emilius in my apartment. My wife did something better. She was able to find a relic of Saint Emilius, which I also proudly known, and again, since you never know, has been hung in my apartment. I want also to stress that the public was also, general people were not aware of the way earthquakes take place, even after the war, Second World War. This is something I'm very curious of, a Mickey Mouse strip from 55, and there was a story about Donald Duck being worried about an earthquake which would strike in Duckburg, and he was asking an expert, and the reply of the expert is the reason is gases accumulating in cracks in the earth as long as the earth shrinks. 1955. The general public was stuck to that. So one issue is seen from seismologists, but also from earthquake engineering side, is how to measure earthquake events. And even here, history is particularly funny. This is an old instrument from China to measure earthquake occurrences. There are metal balls being moved by the shaking and calibrated in such a way that a kind of measurement can be taken. Reason to pride to have considered something similar with the theoretical assistance of my daughter and a colleague for manufacturing it. This is a series of marbles resting on small holes with a calibrated diameter in such a way that different intensities could move a ball, the marbles. Unfortunately, Ispra, or fortunately, Ispra is not particularly a seismic zone, so I can claim that I never measured an earthquake. But sticking to the way we deal with earthquakes, to the measure of earthquakes, I recall the basics of that. Sorry to use a crude terminology with respect to the way seismologists see it. But okay, two fundamental measurement systems are magnitude and intensity, which is what is typically reported by the news when an earthquake strikes anywhere in the world, and typically in an inaccurate way. What are they? Very simply, magnitude measure in a complex way, but I'm an engineer, the energy activated by the earthquake, whereas intensity measures somehow the effects. Are they related? First of all, magnitude can be used worldwide, and is a global concept. In fact, you might remember not many years ago, that man with the strange haircut was testing a nuclear weapon, and all the world was informed about that because seismologists measured some movements all around the globe, and they were able to relate that event to the energy of the weapon of that gentleman. Intensity is something related to the effects, I said, and it is a rather crude system. You might be familiar with it. It is simply a more or less accurate list of effects, ranging from nothing to some levels of damage to extreme damage. So it is something for dispersed measurements. You can travel all around the affected area and see how the damage is spread. So you might recall the ideas about attenuation that Camilla was introducing. So it is a rather crude, one might say it's stupid measurement, but it is very effective to map the distribution of shaking without a refined grade of instruments. Are they related? In the news, typically you hear the wrong sentence. An earthquake happened which had a magnitude of that much, which is equivalent to an intensity of. This has no meaning for a simple reason. The energy is released at the place where the plates move, which might be more or less deep or shallow. So that simple consideration means that there is no precise correlation between magnitude and intensity. A very deep event with a lot of energy might shake all the globe but cause little damage to your home, whereas a very shallow earthquake with little energy, little magnitude might cause a lot of damage because it is exactly under your chair. So again, no simple correlation. That means that intensity and the magnitude are reference measurements for engineers, but are not practically used in design. First of all, engineers have a very clear conviction, which was somehow reflected by Camilla's talk. There is no way to reliably predict earthquakes. You can, to some extent, forecast where they might happen, but the possibility to predict that tomorrow at 3 p.m. an earthquake will strike Ispra, so we might not care about the safety of our building because we might just stay outside, is a science fiction. Taking that into account, the very simple task of earthquake engineers is to design structures which are able to resist the earthquake with the characteristics which might be defined by seismologists, but without a time reference. This is done now by seismologists by studying microplates. They call them seismogenetic areas, but that is not my discipline. But the knowledge is enough to predict what the maximum level of earthquakes can be expected in each point of a territory. As Camilla said, there are a lot of issues affecting the ground shaking. Camilla listed 3 groups. I can do more. There is a propagation in the bedrock, but then there is an interaction with the soil types, because typically alluvium and rocky layers might be present, and reflection, refraction of the wave all throughout these layers cause a complex system which might be studied, and that is what we call soil amplification. Then there is the interaction of the wave with the foundation, and from the foundation with the structure itself. So there is quite a lot of aspects which should be taken into account, which might correspond to mobilizing different competencies. So we have seismologists defining what kind of wave might arrive. Then we have people who are experts in soil mechanics, which can study complex systems, there's effects there, and there are people dealing with the interaction between foundation and finally the structure. So I said that intensity and magnitude are not the tools adopted by structural engineers. So what is the measurement we adopt? You heard that, it's acceleration. Acceleration is a tricky concept. In spite of the fact that our body can feel acceleration, we have something in our ear which works more or less as a gyroscope, whereas we cannot feel velocity. Surprisingly, everybody knows what velocity is. 50 kilometers per hour is high velocity, mainly if you're fine. Whereas I challenge everybody to tell me what acceleration is in simple terms. And is 10 kilometers per square second a low or a high value? Well, engineers have to deal with acceleration of the ground. Why? for a very simple reason. Newton's law. If you multiply the mass times the acceleration, you get a force. And the force is what typically we reason with. So peak ground acceleration times the mass of the buildings is a force. Is it the end of the story? No, obviously it is not. First of all, let's look at the quantities. This is an accelerogram. You saw some already. This is historically the first earthquake which activated earthquake engineering, a Californian earthquake, which surprising is the most representative for many reasons, but I will not stick to that. What value can you see there? 0.3 G. 0.3 G. That was recorded during the 1940. I said that activated the very concept of earthquake engineering because it is quite a high value, isn't it? But there is something more. I said the peak ground acceleration times the mass is not the only force which might be suffered because there is the dynamics, the response of the building. And to explain that, I stick to a swing. Dynamics means that time matters. If you push the swing with the right frequency or period, the amplitude of the swing increases. Instead, if you do that wrongly, with not in phase with the previous motion, it might even reduce. That introduces a concept which is very important in earthquake engineering, which is the response spectrum. Response spectrum for a given earthquake is the acceleration suffered by a structure according to its frequency or period. That's the dynamics of a response. And what do we learn from that? First of all, that there are quite huge values. For the famous start of my activity in earthquake engineering event, the Friuli earthquake, a peak was 1.2 G, means 120% of your weight acting horizontally. But it is not all, because we said it depends on the frequency or the period. So we learned that for very rigid structures, there is no amplification, we say. The maximum acceleration is the one at the ground level. Whereas for high buildings, there is a smaller amplification. So for this kind of event, skyscrapers suffer much less than a single-story house. For even softer structures, and the building is such, it has very long vibration period. The amplification is severe. It suffers very little in terms of forces for the earthquake. You might be thinking about the Messina Bridge. Is that all? No, it is not. There are other problems. But in terms of forces, bridges are not typically much exposed to earthquake. Where the problem remains is typical medium-rise building where the amplification is typically of the order of 2.5 times the peak ground acceleration. If we look at stronger earthquakes, this is the L'Aquila earthquake, we see even larger values. Maximum acceleration, maximum spectral acceleration of the order of even 2 G. Again, that means a force of 2 times the mass of the buildings acting horizontally. How can a structure resist that? Simply, it cannot. Sorry? No, this is the acceleration which is acting at the building level, suffered by the structure because of a swing effect. It is more or less of the one coming from the soil. We might swap to discussion, do you mind? So I said, can a building resist the horizontal force of even 2 times for L'Aquila, not for Chile or Japan earthquake? Can it resist such a force of 2 times its mass horizontally? No, it cannot. And what happens then? We recall a very simple concept, the Hooke law. The force is proportional to the deformation as long as the structure remains elastic. If you have a spring, you apply 1 kilo of force and you measure 1 centimeter. 2 kilos of force, 2 centimeters, so on and so forth, forever. No, at some times it will damage and the force will not increase anymore. That's the trick. We might surrender, imply that buildings do suffer damage, and we have to take that into account. They enter in what we call ductile behavior. Ductile means not elastic anymore. You reach a maximum force, then there is an elastic limit, damage increases, displacement, deformation increases, but not force. That's the way in which ordinary structure can survive, which opens a problem. How much can we deform our structure? What is the level of damage we can assume and tolerate? If you think about paperclip, you know you can deform it at a lot. How many times? How much? Those are difficult questions which mostly depends upon the material. There are stiff structures, very rigid. There are soft structures, but there are strong structures and weak structures. There are many ingredients. We have a portfolio choices about how to design our structure, admit more or less damage, more or less force. So how can we design our structure then? Because what we want as a requirement is rather complex, because we want our building to resist the earthquake. What does it mean? Not easy. We want that our structure, in case of a small, very frequent earthquake, will suffer no damage. And for a medium strength earthquake, a level of damage which can be repaired. And for the maximal possible earthquakes predicted by Camilla, we want the building not to collapse. So a portfolio requirement with a portfolio of design choices, stiffness, strength, ductility, with one material, the other, a mess. That's why engineers do not follow the very functioning of a structure during an event. They rely upon design rules, codes. That's where earthquake engineers are active, reverting knowledge about the very complex behavior to a complex structure to different earthquakes to simplified rules for designing. Well, that's where earthquake engineers are active. What is implied? First of all, the way the energy is dissipated must be controlled. What we say is that we should obtain a structure which we call it mechanism, the way it is damaged and moves not elastically anymore, in a way which in which beams are damaged rather than columns. We call it global mechanism. The beams suffer damage, they rotate a lot, but columns remain undamaged, which is opposed to what we call story mechanism, in which damage is concentrated and stability might be prevented. This must be implied in all design rules, and the design rules should enforce this sort of functioning. That's where the combination of numerical studies, investigations after earthquake. I have a long career of going to places affected by earthquake, study what happened, but also learning from experiments drives the development and calibration of these simplified design rules. This was one of the objectives of the laboratory I have been dealing with, the ELSA laboratory, which is one of the ways we can study what happened when an earthquake acts on a structure. The simplest is the shaking table. I'm sure you know what a shaking table is. Conceptually, it is a washing machine causing the movement of a platform in which you mount your prototype and see what happens. You see a very large one, the one of the University of California, San Diego, and here you see an experiment on a shaking table, which obviously doesn't work. Like that. As you see, you activate the shaking table, the earthquake happens, and you see what happens. Fortunately, you measure because everything takes place in a few seconds. The main limitation is that the size of the shaking table is typically reduced, so you cannot accommodate a real building to see what happens. This was the equivalent of a test done in our laboratory, done instead in a shaking table, and you see that it is not fully representative of a full construction, but still you can learn a lot. What we used in our laboratory here in Ispra instead is a different approach. It is called pseudo-dynamic test method, and I will not spend many words on that. It is a complex system of simulation in which computer simulation interacts with the measurement, and the result is that the structure is subjected more or less exactly to the same history of deformation, which might result from the earthquakes, but in a distorted time scale. So an earthquake, which typically takes 10, 15 seconds, is reproduced in hours, which allows for large specimens from one side, and also gives the freedom of carefully monitor what happens, measure here and there. So there are two experimental methods which are sometimes complementary: a real-time test on a shaking table, or a pseudo-dynamic distorted time experiment on a larger, possibly full-size structure. It has a lot of advantages. For instance, you can limit the experiment to what is of your interest. We have been testing bridges. Bridges typically suffer damage in the pier, not in the deck. The deck is heavy and rigid. It does affect the response of the structure, but it does not suffer damage. So it can be modeled numerically. And you can limit the test to where the damage takes place, the piers. And we have done that in our laboratory, simulating a 250 long bridge without having the decking and the bridge in the laboratory, but just the piers. And I can claim that there have been many projects in which the community of earthquake engineers have been active for getting information, which are in turn pumped into numerical models, and numerical models are used to run extensive simulations to finally calibrate what is the result, those simplified rules for design. This is something I'm particularly proud of for many reasons. First of all, it is the largest building having been tested in the world, and that was done here in Ispra. The reason for being large was to have it full size, but also to test different arrangements in the same structure. But what I'm particularly proud of is the fact that this really solved a big problem. You might remember that a few years ago, a small earthquake struck Emilia region in Italy. First of all, it was not a region classified seismic, which is a shame, but it's not a responsibility of earthquake engineers. What was more important was that, strangely, precast, prefabricated structures were mostly affected and resulted into the largest toll of victims. We had to admit that the way we designed those precast structures was not adequate. We had to develop new rules, and that was the response. A series of tests done on precast structures to study the behavior of each sort of possible connection and derive the necessary rules to be used in the codes. Here you see an accelerated motion, and that corresponded to the presence of a wall, but in this configuration was not part of the response. This was another activity which was to address one of the most important problems now, whereas we can claim that the way we design structure is safe enough. Large uncertainties do exist for non-seismic structures. What to do with structures which we know are not safe enough because they were designed and built at a time in which the knowledge was not sufficient. You should improve their strength or ductility, but that is not an easy game. But series of tests was exactly to study possibility to improve the behavior of a typical building of the 1960s by adding a wall and to derive rules about how to design the connection of this wall with the existing poorly performing structure. This was another complex activity on the same topic, a non-seismic building rehabilitated in the different ways. In this series you see glass fibers, composite structures, layers being put to improve ductility, and that was only one of the activities we did. What is impressive here is that you see the full complex response of an irregular structure, because earthquakes have 3 components at least, and irregularity of the building might introduce torsion. Those are complex components which was addressed only in this series of experiments. I think this is the last one. This is for something smarter. The idea here is to, once you assume that the damage has to suffer damage because it has to dissipate the incoming energy, is there a way to concentrate the place where the damage is dissipated? That's the idea. We call it K-bracing, and in the K-bracing there is an element, a sacrificial element, which takes all the damage, dissipate the energy, preventing the rest of the building from suffering any damage. The concept is that after the earthquake has stricken, you replace that element, you go to IKEA, buy a new one and mount it there. And those, okay, the concept is sound, was not even relatively new, but the very possibility of activating this replacement had to be tested, and I explained why the size of a specimen and the stress on the testing activity. Sorry. No, I'm going the wrong direction. Okay, the last issue is again about smarter ways to protect the earthquake, the structures from the earthquake. And again, I revert to Disney cartoon. Once we say that, and Camilla clearly said that, it is not earthquake that kills people. Earthquakes are a natural phenomenon, and damage is a responsibility of a building. Why don't I protect the structure from isolating it from the ground shaking? And that's the idea. If we could lift the structure, the ground might shake, but the building would not suffer any force. And this is done in practice. We use typically laminated rubber bearings, which are layers of rubber, which are very flexible in the horizontal direction, still stiff in the vertical direction because the weight of a building has to be sustained. And this is the concept. By doing so, you can protect the upper structure from forces and then from damage. And it illustrates again this idea that the matter is the building willing to remain still as a consequence of a ground motion, not the other way around, which is typically how we imagine it. The idea is very smart, and it has been used enough extensively. Obviously, all the technical arrangements corresponding to the solution might be costly. Okay, that's somehow the end of the history. What I want to claim is that there is still research to be conducted. I want to recall that the matter is complex and will remain complex. What we need is not a way to study the real functioning of buildings, but rather more and more reliable, simplified rules to design our civil engineering structures. And that is where earthquake engineering community is active and will remain active. Thank you.